Now, before we start talking about work and energy, we need another mathematical tool. In an earlier video, I talked about adding vectors together and multiplying a vector by a scalar, which just changed its length. All right, now we need to know how to multiply vectors together. And there's two ways we can multiply vectors. One is called the scalar product because the result is a scalar, not a vector. This is also called the dot product. The other way to multiply vectors is called the vector product, and because that results in another vector. We'll save the vector product to a later time, and right now we're going to look at the scalar product, or also called the dot product. It's called the dot product because of the notation that we use. So we see here, I take vector A dot vector B. The result is the magnitude of A times the magnitude of B times the cosine of the angle between them. So if I know the lengths of the vectors, I just take the length of A times the length of B times the cosine of the angle between them. Now, if I have the vectors in component form to do the dot product, I multiply the x components together, multiply the y components together, and multiply the z components together, and then sum those three products. That gives me the same result. Another way to look at the scalar product, we see that when I do the dot product between two vectors, I get the projection of one vector onto another. So in the top diagram, I see the component of vector B that points in the direction of A is B cosine theta. So I can take the length of A times the component of B that points in the direction of A, which is B cosine theta, and multiply those together. That gives me the dot product. Or in the bottom diagram, I see the component of A that points in the direction of B is A cosine theta. So I can take that length, A cosine theta, times the length of B. So I get the projection of one vector onto another. All right, let's look at an example. We are given two vectors, A and B, and we want to find the angle between them. Vector A is given as 3.0 I hat minus 4.0 j hat. Vector B is 2.0 I hat plus 3.0 k hat. K hat, of course, points in the z direction. So doing the dot product, A dot B, I get the length of A times the length of B times the cosine of the angle between them. Well, we can find the length of A. We just use the Pythagorean theorem. So it's the x component squared, 3.0 squared, plus the negative 4.0 squared, and then the square root of that, which gives me 5.0. And then to get the length of B, I take 2.0 squared plus 3.0 squared, and then the square root of that sum, and I get 3.6. So now I've got the length of A and the length of B. Now I can do the dot product directly. So I got 3.0 I hat minus 4.0 j hat dotted into 2.0 I hat plus 3.0 k hat. So when I do the dot product from the components, I multiply the x components together and the y components together and the z components together. So I multiply the x components together, so I have 3 times 2. Now multiplying the y components together, I have minus 4 times 0, because vector b doesn't have a y component. And then I multiply the z components. Well, vector A z component is 0, so I have 0 times 3. So I have 3 times 2 plus minus 4 times 0 plus 0 times 3 gives me 6. Now the angle between them then is going to be the inverse cosine of the dot product, which is 6 divided by the product of the magnitudes, 5 times 3.6, and I get 71 degrees. All right, so again, the work done by a constant force moving an object through a displacement is given by the component of the force in the direction of the motion times the distance that the force moves the object. So looking at the diagram here, we see we're doing the dot product of the force and the displacement. since the component of the force in the direction of the motion is F cosine theta, and then we multiply that by the displacement d, that's the same as the dot product of the force and the displacement. So in general, for the work done by a constant force is the force dotted into the displacement. So also notice that there must be motion for work to be done on the object. If the force doesn't move the object, the force does no work on the object. So there must be motion for work to be done on an object. And so it's the force dotted into the displacement. So two things must happen for work to be done. There must be the application of a force, and something must be moved by that force. So work gives us a way to quantify what happens when we apply a force and succeed in moving something by that force. So looking at this diagram, we see a woman holding a barbell above her head. Well, the work done on the barbell to lift it up in the air is the average force you must apply to lift it times the vertical distance the barbell is lifted. So again, there must be motion for work to happen. So there must be something moved by the force for work to be done. Now work can fall into two categories. One is work done against another force, and the second, work done to change the speed of an object. Think about the previous picture where he showed a woman lifting a barbell up in the air. She's doing work against the force of gravity. So the force of gravity acts down, so she's lifting the barbell up. She's doing work against the force of gravity. That's the first kind. The second kind, work to change the speed of an object. Think about throwing a baseball. When you throw a baseball, initially when it's in your hand, it doesn't have any speed, right? It's at rest. You apply a force over the distance that you move your arm, and then you give some speed to the baseball. So you've done work on the baseball to change its speed. Similarly, the braking force in your car can slow the car down to change the speed of your car. So it's the braking force changes the speed of your car. So the work done by the braking force changes the speed. Now, if there are several forces acting on an object, the total work then, or net work, is found by one of two ways. The first way is we could find the work done by each one of the forces and then simply sum those up. So that's what's shown in the first equation. I take the work done by force 1 plus the work done by force 2, etc., and just add all those together. The other way to do it is I could find the net force. I take the vector sum of all the forces acting on the object and then find the work done by that net force, and that gives me the same result. But the thing to remember here is work equals the net force dotted into the displacement, force dot displacement. But this is only for a constant force. If we have a variable force, we have to do something different, and we will discuss that in a later video. But for right now, if we have a constant force, we take the force and dot it into the displacement to get the work. So now we introduce what's called the work-kinetic energy theorem. If I have a constant force in one direction, I can write that force as ma, where a is the acceleration. And if the force is constant, the acceleration is constant. And we'll do this in just one direction, the x direction. Now, since our acceleration is constant, we can apply the constant acceleration kinematic equations that we developed earlier. So the one where the time is eliminated, we have v squared equals v naught squared plus 2a delta x. Now I solve for the acceleration, and I get the acceleration equals v squared minus v naught squared over 2 delta x. All right, so now the work then is the force in the x direction times the displacement, which is delta x, and I can write the force as ma, so I have ma delta x equals the work. Now I'll substitute the acceleration for the expression we found above. So we get the net work equals mass times the quantity v squared minus v naught squared over 2 delta x, and then times delta x. So the delta x in the numerator and denominator divide out, and then multiplying the m through and separating the terms, we get the net work equals 1/2 mv squared minus 1/2 mv naught squared. All right, now we define kinetic energy as the energy possessed by a moving body. And we use a capital K for the symbol for the kinetic energy, and it's equal to 1/2 times the mass times the square of the speed, or 1/2 mv squared. Now notice that kinetic energy is a scalar quantity, so it's not a vector. Velocity is a vector, of course, but speed is a scalar quantity, so kinetic energy is a scalar. Also notice that kinetic energy is always positive. So no matter what direction the velocity is, the speed is always just the scalar portion, and when we square it, it's always positive. So based on the previous slide, now we have the work-kinetic energy theorem. And that states that the net work is equal to the change in the kinetic energy. So the net work done on an object is equal to the change in the kinetic energy of the object. So note this is the net work. So we must include the work done by all forces acting on the body. All right, now think about kinetic energy. This is the energy possessed by a body simply because of its motion. Now, suppose I toss a baseball to you very gently. It's easy for you to catch the baseball. But what if I threw a 90-mile-an-hour fastball right at you and you didn't have a baseball glove? It's going to be really hard to catch that. In fact, if it hits you, it's probably going to hurt. So we see that the faster something moves, the more energy it has. So what is the kinetic energy of a baseball, which has a mass of about 0.15 kilograms, with a velocity of 40 meters per second, which is about 90 miles per hour? So the kinetic energy, we write 1/2 mv squared. So the 1/2 we can write as 0.5. Then we have the mass, 0.15 kilograms, times the speed, 40 meters per second squared, and I get 120 joules. So that would be the kinetic energy of my 90-mile-an-hour fastball. Let's look at the units. Okay, we have mass times speed squared. Well, mass, of course, is a kilogram. Speed squared is meters squared over second squared. And so I have kilogram meters over second squared times meters. Well, a kilogram meter per second squared is the same as a newton. And so I get a newton times a meter, which is a joule. So you can see how the units all work out. Now, work can be positive or negative. So work is energy transferred to or from an object or system of objects. When I transfer energy to the system, I do positive work. And when I transfer energy from the system, we do negative work. So work is positive when the force is in the direction of the displacement, and work is negative when the force is opposite to the direction of the displacement. Another thing to notice is remember that kinetic energy was 1/2 m times the square of the speed. So kinetic energy is always positive. Kinetic energy is always positive. But the change in kinetic energy can be positive or negative. So when the object slows down, the change in kinetic energy is negative, and when an object speeds up, the change in kinetic energy is positive. So when you throw a baseball, the speed of the ball goes from 0 to 90 miles an hour when you throw a 90-mile-an-hour fastball. And so its kinetic energy increased, so the work that you did was positive. You transferred kinetic energy to the baseball. You increased its kinetic energy. When you catch the baseball, so the catcher catches the 90-mile-an-hour fastball, the speed of the ball goes from 90 miles an hour to 0, so the catcher does negative work and removes the kinetic energy, so the kinetic energy decreases. So here's an example. A 1,000 kilogram car at 40 miles per hour, or 18 meters per second, brakes to a stop. How much work is done by the braking force? Assume a constant braking force. So we apply the work-kinetic energy theorem. The net work equals the change in kinetic energy. And we're going to go for final kinetic energy is 0. Our initial kinetic energy, 1/2 mv naught squared. And so we get a negative 1/2 times the 1,000 kilograms times the 18 meters per second squared gives me a negative 162 kilojoules. So when I brake the car to a stop, the net work is negative because the kinetic energy decreased. The braking force did negative work and removed the kinetic energy from the car. All right, supposing you're driving your car down the street and you need to come to a stop. You apply the brakes and you come to a stop in a certain distance. Now, what happens if you travel twice as fast? How does that affect the stopping distance? And assume a constant braking force. Let's take a look at that. So let's apply the work-kinetic energy theorem. The work equals the change in kinetic energy. Final kinetic energy is 0. We've come to a stop. The initial 1/2 mv naught squared. So I have 0 minus 1/2 mv naught squared. The work we can write is the braking force times the distance, and that's equal minus 1/2 mv naught squared. If the force and distance are parallel to each other, so we just get negative F dot D. Since the force is opposite the direction of the motion, we get the negative when we do the dot product. So minus F dot times D equals minus 1/2 mv naught squared. And we see then that the distance is proportional to the square of our speed. So it takes 4 times the distance to stop. So when you drive twice as fast, it's going to take 4 times the distance to stop your car. This is why we have 20-mile-an-hour speed limits and school zones at the time when the kids are out, right? When the kids first get out of school, you drive by a school, they've got that flashing yellow light reminding you that the speed limit is 20 miles an hour. The reason is you drive a little bit faster, it takes a lot greater distance to stop your car, right? So twice as fast means 4 times the distance to stop. Since the energy is proportional to the square of the speed, I double the speed, I've got 4 times the energy. So it takes 4 times the work to stop it. All right, to review now, the net work done by all forces acting on an object or system of objects is equal to the change in the kinetic energy of the object or system of objects. Work is energy transferred to or from an object or system of objects. Energy transferred to the system is positive work. Energy transferred from the system is negative work. All right, let's look at the work done by gravity. When I throw a ball straight up, it is slowed down by gravity. That is, the gravitational force does work on the ball. So when I throw the ball, the instant it leaves my hand is no longer influencing the ball. But the ball will have a certain amount of kinetic energy. We'll write that as 1/2 mv naught squared. Now, as it goes up, the gravitational force points down toward the center of the Earth, but the displacement is up. It's moving upward. So when I find the work done by gravity, I take the gravitational force dotted into the displacement, and that, of course, gives me mg times the displacement times the cosine of theta. And theta is going to be 180 degrees, since the displacement and the gravitational force are opposite in direction. Cosine of 180, of course, is -1. So the work then is negative mgh, where h is the height it goes before it comes to a stop. So the work is negative. So that means it's removing energy from the ball, and the ball slows down. Now, what about lifting an object? So when you lift an object, we're applying an additional force. It's our applied force, but yet we still have gravity acting on the object that we lift. So the change in the kinetic energy, K final minus K initial, equals the net work, which is the work done by us, our applied force, plus the work done by gravity. So if I lift, I do positive work because I'm applying a force upward and I move the thing upward, so the displacement is also upward. They're both in the same direction, and so I'm doing positive work. But the gravitational force is in the opposite direction of the displacement, so the gravitational force is doing negative work. So if the object that I lift is stationary before I lift it, and it's stationary after I lift it, then the kinetic energy change, of course, is zero, because it's stationary at the beginning, the k equals 0. It's stationary once I reach the maximum height, k equals 0 there. So the change in kinetic energy is 0. So that means the net work is 0, which means that the work that I do is equal to the negative of the work done by gravity. Since I need that the work done by me plus the work done by gravity must sum to 0, that means the work that I do is equal to the negative of the work done by gravity. So when you lift something at a constant speed, the change in kinetic energy is 0. The work that you do to lift is equal to the negative of the work done by gravity. All right, we're going to look at an example. We have a cable pulls a crate that weighs 60 newtons up a frictionless ramp that's angled at 30 degrees, a distance of 2 meters up the ramp, with a force of 50 newtons. Part A, what is the work done in the crate by the tension in the cable? B, what is the work done in the crate by the gravitational force? C, if the crate starts from rest, what is its kinetic energy? And D, speed at the end of the displacement. Okay, so for part A, we just do F dot D for the tension in the cable. The cable force is a constant 50 newtons, and we're given the displacement is 2 meters, and the displacement and the cable force are both in the same direction. So we just have 50 newtons times 2 meters, or 100 joules. All right, so for part B, what is the work done in the crate by the gravitational force? All right, so we know from before, when we looked at Newton's second law on inclined planes, we saw the component of the force of gravity down the hill is mg sine theta. So now the work is the force along the direction of motion times the displacement. Well, the force is down the hill, so we'll use negative mg sine theta for the component of the force down the hill, and then the displacement up the hill we call d. So we have minus mg sine theta times d. The mg is given as 60 newtons. mg is the weight. So that's 60 newtons times the sine of the angle times 2 meters. Well, the angle is given as 30 degrees. So we have negative 60 newtons times sine of 30 times 2 meters, and we get negative 60 joules for the work done by gravity. All right, so now we want to find what is its kinetic energy after the displacement. So we apply the Work-Kinetic Energy Theorem. We have the net work equals the change in kinetic energy. Well, the net work is equal to the work done by the tension in the cable plus the work done by gravity, and that's equal to the change in kinetic energy, which is the final K minus the initial K. Well, the work done by the tension in the cable we found is 100 joules. The work done by gravity was negative 60 joules, and that means the change in kinetic energy must be 40 joules. Since our initial kinetic energy was 0, we started from rest, the final kinetic energy is 40 joules. All right, now the last part, we want to know the speed of the crate when it reaches the top at the end of the displacement. Well, we've got the Work-Kinetic Energy Theorem that says the net work equals the change in the kinetic energy. The initial kinetic energy was 0, so the final kinetic energy then 1/2 mv squared is equal to the net work, which we found to be 40 joules. So to solve for the velocity, we multiply both sides by 2 and divide by m, and then take the square root. So we get V equals the square root of 2 times the kinetic energy divided by the mass. Well, the mass, of course, was not given. We were given the weight as 60 newtons, but weight, of course, is equal to mg. So the weight divided by g will give me the mass. So when I plug in the numbers, the final kinetic energy was 40 joules, so times 2 divided by 60 newtons over 9.8 for g, and we get 3.6 meters per second. Okay, so that solves this problem. All right, so that will be the end of this video. In the next video, we'll do some more examples of work in kinetic energy. Hi, Dr. C here. I want to ask you to please help support this channel. There are a number of links in the video description to Amazon.com. If you purchase any items from Amazon by entering through these links, even if it's not one of the items listed, I will receive a small commission that helps to produce more content. There is no additional cost to you whatsoever. Also, please leave your comments, questions, or suggestions below. I want to thank you for support of this channel and please subscribe. I hope you find my videos useful.